My guest today is Dr. Atefeh Mashatan. Atefeh is the director of the Cybersecurity Research Lab and professor at Ryerson University. In 2020, she is recognized by IT World Canada as one of Canada's top women in cybersecurity. In 2019, she was recognized by SC Magazine as one of the top 5 women of influence. Glad that she's here with us today. One of the topics that you're working on is quantum computing. First of all, what is quantum computing?
A classical computer, for example, your laptop, your desktop, your phone, your smartphone, your servers, they use bits, zeros or ones to store and process information. A bit is physically implemented by, think of it as electricity that goes on or not. So a current that goes through or not, 0 or 1. Quantum computers are based on a completely different physical architecture. They're based on quantum mechanics, and they work with quantum bits or qubits as opposed to bits. So a bit takes value as 0 or 1. A quantum bit takes a superposition of states between 0 or 1. So with certain probability, it's going to be 0 when it's measured. With the complementary probability, it's going to be 1. We don't know which one it would be until we actually measure it. And because of the difference in the architecture of these fundamental elements of a quantum computer, they store and process information very differently compared to classical computers.
So what quantum computing can it be used for?
So quantum computer would have two sides, a positive side and a negative side. A positive side is that a lot of the problems that you're interested in solving, optimization problems that we cannot solve with our current classical computer capacity, or it would have to take us a very long time to actually solve them, quantum computer would be able to solve much faster. And there are important problems that we want to solve in pharmaceutical research, in solving cancer, in any, some classes of optimization problems that it's in our best interest to be solved. And quantum computer would help us solve them much faster, more efficiently. The negative side of it is that there's some mathematical hard problems that we would want them to remain hard. Problems that are based on integer factorization problem and the problems that are based on discrete logarithm problem that we have basically used to secure the internet, online banking, and so on and so forth. So it's important for us, for these two problems to remain difficult. And unfortunately, for us, the quantum computer would solve these problems efficiently.
Are there any sectors in which quantum computing is more prone to be used than others?
In a positive way, a quantum computer would help any sort of optimization problem. And pharmaceutical industry, solving for drugs for cancer and whatnot, these are positive ways that a quantum computer would help us once we have them and scalable enough to solve those optimization problems. On the other hand, those industries such as financial industry or healthcare industry that are dealing with personally identifiable information, such as your social insurance number, that you would want to protect them and keep them confidential for a very long time. Those need to worry about a quantum computer, not get excited about it, because a quantum computer would be able to break the confidentiality.
So what are the implications of quantum computing in cybersecurity? What are the challenges then of this technology?
Yes, so cybersecurity is using cryptographic techniques to protect the confidentiality and integrity of data. So we use encryption, for instance, to keep information confidential. And we use digital signature schemes to provide integrity on data. And currently, standard ways of doing digital signature schemes and encryption schemes are using public key infrastructure, public key crypto systems, and currently public key crypto systems, the ones that are standardized by NIST, National Institute for Standards and Technology, or ETSI, its European counterpart, they're all based on public key crypto systems that are vulnerable.
So quantum computing can, in fact, break these crypto systems. This is what I understand.
They would be able to. So right now, the quantum computers that exist, they're not scalable. They're not attack capable. And we have some engineering challenges until we make them scalable enough so that they can attack. But once we overcome these engineering obstacles, they would be able to attack these crypto systems that we are using to protect online banking, protect internet, protect confidentiality and integrity of our data in these two specific industries, such as healthcare and financial industry and others.
So the idea is that if quantum computing is not put in the right hands, it can be some kind of threat, right?
Absolutely. So we don't have any indication in the public that a scalable quantum computer exists as of now, but it could happen in the future. And what should worry executives who are custodians of PII data with long shelf life, so social insurance number that you want to keep confidential for more than 10 years, is that with a high probability, we may have a quantum computer that is scalable enough to break these in the near future. So some of the data that we are protecting now, we would want to have it remain confidential in the next 10, 20 years. And the next 10, 20 years, with some good probability, we could have a quantum computer that can break it. So if the information is harvested now, it can be broken in, the encryption can be broken in 20 years from now. And that information may still be valuable to an attacker and to the owner of that data, even if it is harvested now and decrypted 20 years from now.
What should financial institutions learn about it, and what should they do?
Again, that's a very good question. So they need to do some risk assessment on all of the data that they have. And this is something that they do regularly for their operations, for the security of their operations anyway. They need to empower their risk assessment processes to make sure that they know which cryptographic algorithm is sitting exactly where and how vulnerable it is. And have a roadmap, a quantum transition roadmap that allows them to transition from quantum vulnerable systems to quantum resistant techniques. So there's all signs are showing that everyone is looking into this direction, making sure that they're ready to prepare. They're preparing themselves to be ready when the announcement comes that, well, somebody on the surface of the earth has this and is scalable enough to attack your existing crypto systems.
Dr. Atefeh, thank you for being with us today.
My pleasure. Thanks for having me.